soon be going to, he doesn't have it.
Yeah.
You do? No, you do.
Yes, I do.
You do?
Yeah. I went to Puerto Rico. Not for vacation, for work. I know, it sounds weird.
No, it's not here.
Okay.
So we'll start and you have 30 minutes.
Okay, thank you so much for the invitation, and it's great to be here. A lot of interesting people to meet, to talk. And this is a very interesting, of course I did it, I have to say interesting, right? Work that we developed, but it's important to mention my collaborator, of course, Professor Green, my friend and mentor, of course. And then the collaboration with Professor Faust, Purdue University, and Professor Daniel Killian at Rice University. That's going to be the last part of the talk. So today I'm going to talk about what happened when you have an impurity in a BEC, but not a charged impurity, a Rydberg impurity. I'm sorry for that, for the organizers to give this kind of talk, but I will show you that even when you have Rydberg, still you have some kind of charge there that can be interesting. So today I'm going to discuss 4 different points. I'm going to talk about Rydberg physics, what happened, I'm going to introduce single Rydberg atom in a BEC. Then I will talk about chemistry and some impurities that can be opportunities, like that. So let's start with the Rydberg physics. Rosario already explained what is a Rydberg atom, and sorry, I went to the same. So a Rydberg atom is just an atom with the electron is in a highly excited state. That's good, right? But what's interesting is to keep in mind that classically the orbits of this electron look like that. So the lower the angular momentum, the more elliptical it is. The higher angular momentum, more circular it is, something that some people get mistaken all the time. Of course, quantum matter people do that all the time. So the reason I always say that if there's some quantum matter people, keep this in mind. So as I say, this is a kind of very interesting scaling laws that these guys have. And that can be very interesting for quantum information or chemistry and stuff like that I'm going to discuss today. But what I would like to do is to introduce a very old experiment. And this is what I think from the very first work about Rydberg molecules or Rydberg physics as we know today. So these guys in 1934, they measured the spectrum of alkali atoms when they are in a hot vapor of H2 or N2 and hot temperatures. And they observed, of course, sorry, this is in Italian, of course, these are Italian things, of course, in Italian, so this is potassium and sodium, this is you understand, right? So what they check is the shift of the lines depends on the density of the background gas. And then these guys, they were very smart by the way, they think, well, maybe this shift is only due to the interaction between the core and the neutral. And they did this, they got this. You see it's kind of bad, right? But then there's that very same year, another very, very smart guy, Enrico Fermi, came up with the idea that what is behind this behavior is the electron, the Rydberg electron, colliding with the neutron. And turns out that at that time, they already have more than 10,000 neutral atoms within the Rydberg orbit. So you really don't need to go to a BEC to explore this kind of physics. But the key point that I'm going to show in the next slide, what Green, Professor Green, Hossein, Dickinson, Cheryshev, Kuskobazzi, and Hamilton, and Fabricant, I think I didn't forget anyone, just in case someone gets pissed off, if I haven't, I mentioned all of them. They discovered, well, maybe if this shift is due to the scattering depth, if we have a negative scattering depth, maybe we combine the neutral with the core, right, with the Rydberg. But of course, at hot temperatures that cannot happen because the binding energy is going to be very small, and at 100 Kelvin or 300 Kelvin you destroy everything. But then this guy said, well, let's take the advantage of the ultra-cold physics. In that case, the kinetic energy of the atoms is very small. So maybe you can really form the molecules. And this is what one of the trilobite molecules that Rosario introduced, and the butterfly molecules look like that. Why it's called trilobite is because it looks like a trilobite, and this looks like a butterfly. That's it. The guy that did it came up with those names. Very, very beautiful names, by the way. So I would like to show you where these guys come from. So this is the potential surface for a 53S rubidium atom colliding with a 5S. The butterfly guys, this looks like the butterfly, are the bound states here and here. The trilobites are the bound states here or here. This halogenic, the halogenic uniform due to the high angular momentum component. But as Rosario also mentioned, the previous talk, I think that Rosario did already everything, so I feel bad. So these guys, you make a swing, they have some kind of wheels, And maybe you can think, well, if these ribbons are kind of deep enough, maybe you can also have bound states. And indeed they do. In Stuttgart, a few years back, they did an experiment where they observed by very first time dimers, tetramers, even pentamers. So you can, if you have density enough, you can put as many atoms as you want to there and form like kind of a macro atom or whatever you want to call it, whatever fancy name that you can come out to publish in Nature, whatever. So this is what this guy did. This is an proof that these guys really exist. And of course, I have to say that 2 years ago, the third body was observed, and last year, the butterfly molecule was observed by Herman here in the audience. So now I'm going to talk about single atom in a BEC. Well, before that, I would like to show you this picture. This picture shows like, I'm going to use the term phase diagram. People use it all the time and it's wrong. This is not a phase diagram, this is just a beautiful plot, that's it. Well, we have density as a function of the principal quantum number. Because here there's no entropy included and there's nothing like that. I mean, you have to be very serious if you want to talk about quantum translation and stuff like that. So this is not. This is just a beautiful plot with 3 different colors. But what matters is how compares the interparticle distance with the rest of energy lengths in your system. So in this case, we have one color when the interparticle distance is way bigger than the Brochet radius. Okay, nothing interesting happened there. Then we have this kind of white thing where the interparticle distance is in between the real blockade and the Rydberg radius. But then we have the yellow thing that is going to be our beautiful color today, where the interparticle distance is way more than the real radius. So what is going to happen in this regime is we're going to have a bunch of neutrals within the Rydberg radius. Exactly the same as Fermi did 100 years ago, kind of. But the same, but with the new technology that we can explore better than what they did. And in 2013, the Manfaus group were the first to impressively couple an electron to a Bose-Einstein condensate. So what these guys did in that year was to generate one single Rydberg excitation here in the middle of a BEC. And they observed what happened. And then what happened was something amazing. They observed quadruple oscillations. And they observed also that the number of atoms of the BEC gets lost as a function of time. So it means that there has to be a strong interaction between the Rydberg electron and the neutrals forming the BEC. This is what they observed. And also, they measure stuff like the line shift, the lifetime, and the losses. In that particular work, the authors assume that the losses of atoms are due to a coupling between the phonon modes and the Rydberg electron. That was their assumption, and the feeding works pretty well, and they can explain the results, but assuming some kind of decay time. But what I care today is about this part. At that particular paper, this was an observation. Something interesting, that if you go to the same principal quantum number, and they did the experiment in the thermal cloud, let's say, not still in the BEC, the lifetime gets reduced by almost 2 orders of magnitude you do in the BEC. So the same system, at different densities, behaves totally differently. So, Fermi and all these guys did back in the 30s, we are in the same situation here. So something has to be going on. I mean, something has to going on with all these neutrons within the Rydberg orbit. And now, what I want to ask is why and how this happens. I want to know why this happens, because this is a fact. The experimental file was observed, but no one tried to explain it. Well, we did it. Well, we tried. So now what I'm going to do is this chemistry behind the scene. So this is experimental setup. I mean, Florian is here. He's the boss on this. I mean, he knows all this way better than I do. Sorry if I do something wrong, but okay. This is the two photon transitions that they're using to go to ice state. And what's important here is not about the complicated experiment that is already amazing. It's about the density and the temperature. And analyzing that, what we feel is we are here. So we are in the kind of principal quantum number that we're going to study today, and the density we're going to be all the time in the yellow region. So all the time we're going to have at least one neutral within the Rydberg orbit. Let's see what happened. So now I'm going to show you the curve with all the potentials. So this is the Fermi potential, as Rosario said. This is the P wave component, because rubidium has a shaped resonance. When I say rubidium has a shaped resonance, meaning that the electron colliding with rubidium in free space has a shaped resonance and given kinetic energy, collision energy, sorry. And this is happening with rubidium, happening with cesium, but there are other atoms that they don't have it as a strong input. That is something I'm going to explain at the last of the talk. This is what I mean by shaped resonance or orbiting resonance. It depends if you are a chemist or you are a physicist. They use different language, I don't know why, but that's life. So this is, again, how we can calculate that. And something that we checked before that, it was, we measured what they measured. I don't know how to measure that, of course. They measured the spectrum of a single Rydberg excitation, the DEC. And it turns out that in order to explain the line shape, we really need to include the P-wave shape resonance information. So it seems that really in the DEC, the guys are so close enough that we can explore that short range part of the Rydberg neutral interaction. So then we were thinking, well, maybe since this P-wave shape resonance matters to the, to the line shape, maybe that's matters for the decay mechanism. And that's what we are going to do right now. So I'm a few-body guy, I'm a many-body, so I'm going to work with the two-body. That's enough. I don't need more. Well, maybe I need, but not now. So let's assume that we put the laser there, in the tuning, and we excite the Rydberg with a bunch of needles there, right? So let's think easily. The guy closest to the core is the first one that is going to win the race. This is a race. I mean, the guys want to go to the core and do something bad or good, like as people call chemistry. So let's assume that this guy is the closest one. So if this guy goes closer, due to the butterfly can do that, or can do something even better. Boom. This is a very interesting step that I'm going to explain afterwards, because this is the explanation of the mixing. But anyway, very interestingly, we can calculate the probability to reach the short region part with this state or that state. With that information, then we can go and see what happens with the short range. Well, in short range, no one cares about Rydberg, no one cares about anything like that, but only what you care is about chemistry. That's the real thing. And turns out that when you are getting closer, you don't care about the electron, what you care is about radium plus colliding with radium, right? And this is the potential energy surface that you have. One Gerade, another ungerade. And it's interesting that when the guys is getting closer, even closer, there's a point where the local kinetic energy, or the difference between Gerade and Gerade potential, is exactly the same as the ionization potential. So from that point on, you can ionize. So the guy is going back and coming in that time, the electron can get ionized, and at the end you can have rubidium 2+. A more pictorial way is this one. Sorry, this is the way to calculate the probability due to we have in that paper. And this is the ionization, how the ionization rate depends on the distance. This is what happened. Another way to see this, that is very interesting, is when the neutral is close to the core, the plus charge can jump. And then that jumping depends on the energy difference between Gerade and ungerade. And turns out that this electron, what it's going to see, is a time-dependent dipole moment. And turns out that you can map this problem to a hydrogen atom in a microwave field. So you can study the same ionization process just as a hydrogen atom in a microwave field. But it's a very old problem and very nice. And something happened. Fireworks, and you have rubidium 2+. This is one of the decay mechanisms that we found. And this is our results. This is our 30 results with experimental results, so we are happy enough after 2 years of collaborations. It was hard, but finally we did it. But now there is more. Also, we can have what is called mixing collisions. And in this case, we were able to identify what's the pathway. As I said before, this guy here can couple to these guys, and the trilobyte states here are going to decay. They're going to end up in this hydrogenic manifold that are really hard to ionize. And this is experimental evidence. Tim and Faust's group, excuse me, what they did is they observed as a function, if you wait until you ionize, they need bigger and bigger electric fields to get rid out of the Rydberg. So it means that there is a change in the angular momentum of the Rydberg. So that was the experimental key to see that is really the mixing what is playing a role. So with that information, we can calculate the P metrics that gives you what is the coupling between the different, this guy with this guy, that one and that one and that one and that one, as a function of the distance. And you can see that can be really huge, the probability of coupling between these two. So when the neutral goes close to the core, it does not react. When it comes back, then it's going to have a high probability to end up here. And that's how we explain the mixing collision, the second decay mechanism. And this is the probability for the different states that we can have. So I would like to conclude this part of the talk just mentioning the 2 different mechanisms that we have right now to understand how a single Rydberg atom decays in a BEC. But so far we can mention about time, and as I said at the very beginning, time is
what we like to explain. So it turns out that when we measure the time for the mixing and for the rubidium tube, we observe something like that. Kind of a threshold behavior that sounds kind of a threshold behavior that was kind of very hard for us to explain. Indeed, right now we cannot explain it. That's the funny thing. We believe that this change here is due to the P wave shape resonance that is doing some quantum effects that we can account for. So what we did, something we can do is, okay, let's forget about the Rydberg electron, and let's assume that you only have the core and a bunch of neutrals. And we can calculate what is the collision time for that. And this is the result. So we see that for given principal numbers, we are okay, but then we can never explain the threshold. We tried to do quantum reflection and stuff like that, it didn't work. So far we don't know why this happened, but now thanks to the collaboration with Tom Killian's group, and Professor Dunning, now I'm going to show you some results that can, because that's another thing that can happen here, now that I'm looking at Richard's Smith, is in many-body physics. Maybe in our treatments, since we are doing a two-body physics, we don't have a many-body effect and something like that, and of course we cannot interpret that. So let's see how it goes. And of course another problem is the typical relation between density shift and the energy, between the density and the energy shift is not applicable for rubidium because we have a P-wave shape resonance. So now, let's move to strontium. Strontium is very interesting for us because it doesn't have a P-wave shape resonance. So whatever reaction happened there should be nothing related with rubidium with the P-wave shape resonance. So then Professor Killian and Dunning did the experiment, well, of course with a bunch of students, of course, to see what happened when you did kind of the same experiment as in Stuttgart, but with strontium, without P-wave shape resonance. And here is the potential, how it look like. Here, this kind of a barrier. This barrier can be smoothed out if you include the persistent potential. So in principle, I was thinking, naively, I have to say, that this guy is going to take forever to react. This guy is going to take forever to reach the core and do something. I was wrong. When they did the experiment, they observed this. They looked for the two different processes as we discovered in rubidium, the two of them, and it seems that the decay rates are kind of similar to these two of them. And something more interesting is the same order of magnitude as in rubidium. So what we did is, well, we don't have P-wave shape resonance, so let's go for the easiest thing that you can do. Let's assume that we have an ensemble of atoms and see how long it takes the first one, the closest one, to reach the core. Now, whenever it reaches, something's going to happen. Either mixing or it's going to happen additive ionization. So with that potential, you can calculate the dilation time, and we see the dilation time has to go to 1 over the density. This is a typical calculation, right? Nothing hard. And in this case, we can use the relation between the tuning and density because we don't have P-wave shape resonance. And this is what we have. So as a function of the tuning, we get a pretty good agreement between theory and experiment. And for me, what's more interesting is we get the right trend. So it seems that the mechanism behind the reaction in strontium is just 1 over r to the 4th potential. At the end, at the beginning, we have a charge. Even we have a Rydberg. So, but only the nucleus within the Rydberg is going to feel that impurity in this case. And now, so we can do a different analysis. We can see what happened where for different principal quantum numbers. And again, we can explain them pretty well. So this is quite impressive. Just with a toy model, just 1 over r to the 4th potential, something that everyone can do, right? Very easy. We can explain that. But still, what is very interesting for us is that the decay rates are the same order of magnitude as in rubidium. And that's, I was thinking, you have to go share and I have to take forever. And the reason it's not. It's just 1 over r to the 4th potential kills everything. And it's pretty fast. So never mess around with 1 over r to the 4th potential. Can kill you. These guys are really, really strong. And the difference is only 50%. That's almost nothing for this kind of experiment. So indeed, so now we discovered how the strontium decay and how the rubidium decay. So now we understand the chemistry and how these things correlate to each other. So this is the conclusion. We can understand this through the chemiionization, that is this guy here, this is the mixing. And also the Rydberg neutral core can explain the collision time and can explain the time that these guys measure. Before finishing, as I promised, I said that impurities can be opportunities. So here we go, the experiment. What we can do what we propose is we can put the laser, but instead to be resonant with whatever kind of Rydberg situation, we can go to one of these butterfly molecules. This butterfly molecule that looks like that and have a huge dipole moment. And what we plan to do is to have a quasi-1D system of these butterfly molecules. The reason why, because it has a high tunability, as Professor Ott already showed in his experiments, you can control the orientation of these guys pretty well with a field of 1 volt per centimeter, thanks to the huge dipole moment that they have. The system, when you create the butterfly molecule, has an intrinsic mix in nature. You have neutrals, you have dipoles. And also, it can be extended to 2D and 3D. So we already start to do some simulations, and we can predict how the density of butterfly molecules change for the different principal quantum numbers. And we observe also that if you do the experiment and you look at the magic angle, this is the angle where the dipole interaction goes to 0. That interaction depends on the long range of the butterfly. So you can really measure the different long range coefficients of these two Rydberg molecules just by looking at the magic angle. And of course, our goal is to study kind of well-known physics, where you have kind of a bunch of butterfly molecules in a sea of bosons and see what happens. Because these guys, even when they have a short lifetime, maybe 10 microseconds, you can say, okay, that's bullshit. Well, it can. But the reason why it cannot be, maybe, is because the strength is huge. So even when the guy is on 10 microseconds, if the strength is 10,000 times bigger than the typical that you can have with two different kinds of atoms, maybe the guy is going to imprint some kind of oscillation, some kind of physics that can be interesting to study, the quantum physics, and of course, out of equilibrium physics for sure. And that's all. Thank you.
This is not a trend. The talks are getting shorter and shorter.
Oh, we are very professional.
It's the Spanish trend.
Yeah, we say so. Now we are on
Questions. I have a few questions, but questions for Jesus. Yes.
Yeah, so you were showing very beautiful potential curves, especially for someone who does electronic structure calculation.
Yeah.
So rubidium curves, who actually produced them? It's not easy, right? It's
Yeah.
a specific kind of way.
You can use, you cannot use any of the code that you used to do. You cannot. What we do is very simple. The funny thing is very simple. What we do is we have this Hamiltonian with the delta potential and the derivative, and we choose the hyalogenic manifold, but including the quantum decay. So what we have is with factor functions. And then we analyze everything with a bunch of different n's, different l's, different m's, you have fields or whatever, and then you get it. But in this case, we use the function method. That's a different technique. It's better for the singularity, because something that Chris and co-workers, Hussein also showed, is in order to prevent the system to get crazy, because we have a singularity. This PVC reference is singularity. You need to include levels up and below your target state.
Oh yeah, you need to include all the spectrum below.
Yeah, otherwise, but the thing is, in order to get the right accuracy, you need to do some
you
tricks.
replace it with something.
Yeah, you need to do some tricks that you learn when you are expecting.
So that kind you use for Strozen, right?
For strontium, they did it, the simulation. Hussein did the simulation for strontium, and it works pretty well. They could measure, the bound state they measured was almost perfectly agreement with the experiment. So, I never did the strontium, but the technique is the same. It's general.
Strontium in some ways is easier.
So I didn't got the microscopic explanation for the decay of the strontium-Rydberg molecule. I understand that 1/2 gives the right time scale, but nevertheless you have the molecular potential curve on top of it. So is it still, can you explain it within the overall picture, or is it just a phenomenological observation that the time scale is given by the 1/2?
I remember the paper about the catalytic reaction where, the potential is going to accelerate. The thing is, the density of this gas is so high that that thing doesn't change, almost nothing. We check that. We have an observation of that guy, it doesn't affect, it can change a little bit, but the results are always more or less the same. So you can change like 10%, 20% most, nothing more than that.
I think my question is if the Rydberg molecule can decay in whatever way to go internally. at closer distances.
Yeah.
But the tunnels then, or what is the...
This is a classical simulation. We don't include that wiggle thing.
Yes, but if you were to include it, could you
Yeah,
still
that-
explain the mechanism in this way?
Yeah, that should be just, I mean, in that case, I
It
have
should
to
be there, right?
Yeah, it should be
wiggle
there.
potential.
So then you can do it a wave packet and see how it transfers. Indeed, it's something that we did with the potential of Hossein and co-workers. They didn't include the one relative for potential, since that they have a hill, but it's not. When you include the C4, they have a small thing, but they can transfer. I mean, you can go through the barrier.
But the P-wave resonances are not there.
Yeah, but still there is overall attractive potential.
With respect to this, one over the 4 potential, don't you actually have a screen charge in there? I mean, you have an electron sitting around there, so you have a screen charge. Are you including the screening in your 1 over the 4 at all?
That would be true for neutrons outside the Rydberg.
No, but I mean, even if you're inside the Rydberg orbit, there's a portion of that Rydberg orbit inside of your radius there. So I mean,
What we did is we choose the closest guy to the core. So that's something that maybe I wasn't clear there. So we have like a sample, like a sample of bunch of neutrons, and we really choose the closest one. We don't include the whole thing. I mean, we also did that. But
I mean, yeah, you include the closest one, but the closest one is, unless the closest one is like 100 Bohr radii away, then you're still going to have some screening from the Rydberg electron. So it's not going to be pure 1 over r to the 4.
But that screening happened in a very short time scale, right? Because that screening only happens when the guy is close to the core. Because if the guy is far away, still the neutral is going to feel the whole charge of the guy. Or maybe I'm getting it wrong.
Well, maybe I'm not understanding what you're saying there.
Yeah.
Go, talk there.
We can go off the wall, sure.
Other questions?
Well, I have an additional question. You look at the Rydberg, I mean, in the first part about rubidium, for example, Rydberg rubidium and the neutral bunch of rubidium atoms. They are in where? Not in the mode, I hope?
In that case, they did in a BEC. So they have the basic and magnetic
Yes,
tracks.
yeah.
Freya can explain better. He's the guy. He's the boss. Doing that, yeah. They did it in the BEC. They also did it in the...
They are in the ground state for sure.
Yeah, they are in stress state.
Can I ask one question? If you could bring the slide where you have the coupling matrix elements, the P matrix elements.
That's the one where you put so many...
Yeah, there's a few in the middle of the talk.
Yeah, okay. This one? This one.
Just in the P matrix.
Yeah. Oh, sorry, the B. Okay, got it. That's the problem when you put so many animations. It takes forever now. Maybe I will need
time. Yes.
Yeah, maybe now is when I need a quantum computer. Now I know why they give money to them.
I think that's the one maybe after this.
Yeah, finally. A quantum computer can do this better, right? More real, more quantum. Okay.
There you go.
Okay, finally.
Okay, so the P matrix elements that you've shown between the butterfly and the ground state and so on and so forth, they're very smooth.
Yes. Yes.
I mean, all these avoided crossings that you're showing, but they're...
All these guys here is one of these wiggle things that when they're getting close
the
enough.
avoided crossings, yeah.
But these guys are in this region. I mean, I have 250 around here. So we're only cutting here. So we are not going there. I mean, these guys is what I showed before. So we did this as
the
a...
energy separation is large.
Yeah. We did this as a Landau Senior. But then when we tried to do that as a Landau Senior, was awful because the guys are so close that you need to do a P matrix. Otherwise, it was awful. I was crying 1 week. Got that. Finally, we did that.
Any more questions? Join me in thanking Jesus.
Thanks.